background and integrated statistical methods, and I think today we're going to develop some of the latter and there are Bayesian methods. So Mike will be here until 5 o'clock, and so there won't be a speaker dinner, but if you're interested in lunch, we'll head out there at that time.
Great, thanks for the invitation. Okay, so what I thought I'd do is talk you through some work that's been ongoing in Cambridge now for a few years. And here are some astrophysics that are relevant to it. Some of the earliest ones which I'll come to later on. It's some while ago now. There's another paper which is missing off here on the bottom, which is a paper we're about to submit on a new generic neural network trainer. I'll come to that later on. So largely this work has been done with PhD students. PhD students, Tom Old, Michael Bridges, and Farhan Feroz, who's still in Cambridge working with me. Okay, so I'll just take you through very basic introduction to Bayesian inference. I'm sure it's familiar to everybody, particularly a cosmological case study. That came out on Friday, so I'll take you through kind of what Planck guys have spent the last few years doing, it seems. Then I'd like to talk through two basic ideas that we've been playing with over the last few years that seem to be quite effective at performing Bayesian inference in an accelerated fashion. First is a means for exploring parameter spaces efficiently, which is an alternative to MCMC, predictable nested sum, which is the first topic. And the second topic is if you can navigate around your space, even at each point in the space, you need to be able to evaluate the function that you're exploring, the likelihood of posterior function. And a way of doing that is to learn it via some machine learning algorithm. In particular, we've taken a rather old-fashioned, but nonetheless very innovative approach using neural networks. And then I'll explain how these can be combined a little bit beyond cosmology. We've applied them also to particle physics, and a joint program which combines these things in a single software package called Boundary, which I'll get to at the end of the time comments. So I don't want to spend long on this, I'm sure. Bayesian analysis, you have a set of data points, and you have a model with a set of parameters, and you apply Bayes' theorem, which simply tells you how to get the posterior as an update from the prior through the likelihood, and the likelihood here encodes all of the information on going from your parameter space to observables and then observables to the actual data. So this encodes the physics and the observational process itself. And the denominator, which doesn't depend on the parameters, is the evidence, which is useful for model selection, which I'll come to in a second. I find this notation really unwieldy, so I generally tend to use P for posterior, L for likelihood, pi for prior, and E for evidence. So this is such a famous formula. People in big companies actually make little neon signs out of it. So this is in the autonomy offices in Cambridge above their dining room. They actually have got a neon sign of Bayes' theorem, because Bayes' theorem let them make all their money. And essentially, for parameter estimation, the posterior is your complete inference. This function contains all of the information you can get on your parameters given the data. It's generally quite messy, but typically people try to summarize it using either positions of peaks and their covariances, and that's fine when you've got something that looks broadly single humps, univariate Gaussian, multivariate Gaussian. And you can also obtain constraints on subsets of parameters by marginalizing in either direction integrated through the posterior. Of course, not all posteriors are friendly. Some of them are more unfriendly. Actually not that unfriendly as compared to the example, but you can see that trying to just use a peak position in covariance like you would with a Gaussian will start having problems when you have, for example, long degeneracies. See this picture here. And particularly bad, you can't really do this too well when you start getting multiple peaks in the posterior, multimodal distributions. Nonetheless, people either try to maximize the posterior using some gradient search algorithm, or better, try to map it out either on grids, which only works up through a few dimensions, or by using sampling methods.
That's parameter estimation. Model selection is sort of the next level of Bayesian inference. Here, you're not so interested in the parameter values themselves, but more interested in which of the set of models, let's just take two for example, are best to describe the data. And Bayesian methods provide quite a neat way to do this because the denominator of Bayes formula, which I just showed you, is pretty much what you want. It's the probability of the data given your model, which I remember I call the evidence. And you can see the evidence is the integral of the likelihood times the prior over the parameter space, or with the unknown right posterior, or you can think of it as the average of the likelihood under the prior. It's not quite exactly what you want. The thing you really want is the ratio of the probabilities of your two models given your data. You can just use Bayes' theorem again, and you see that it's just equal to the ratio of the evidences for each model multiplied by the prior ratio on your models, which is often used, but sometimes it's really complicated. And the idea here is that evidence incorporates Occam's razor principle, so a model is preferred if more of its parameter space is likely, and unfavored if it has large areas of the parameter space with low likelihood values, even if the likelihood value is very high, repeat if it's p-like. And so this is the sort of core of Bayesian evidence, Bayesian model selection using evidence. So yes?
How do you define the probability of each one?
This is the your prior on your model. So often it's unity. So you might, for example, have a couple of cosmological models, say with and without evolving dark energy equation state, for example, and this you would generically set as unity. You don't do that if these are, if you're doing source searches, for example, this might be the probability that there is an SN cluster within a particular region of sky, over the probability that there isn't, then this takes a lot more care, and you have to fold in the mass functions here to calculate this part. So let's take a cosmological case study. Knowing the group I'm in, I hardly need to do this, but so CMB, you'll heard about that on Friday. It's a snapshot, an early sort of childhood snapshot of the universe. When decoupling, it provides essentially a map of the density fluctuation, type of transition. And they're interesting for a couple of reasons. You roll time forwards, and they collapse under their own gravity to form what the structure you see. You roll time backwards, and you have constraints on what form fluctuations in the first place. In other words, an insight into early universe physics, particularly physics of inflation. So it's kind of a surprising kind gift from the universe to give us the CMB. And this is what a typical jobbing CMB analyst spends most of their time doing. This is what when you hear them swearing at their terminals is what they're up to. So you have, and this isn't just related to CMB. Hopefully when I go through this, you'll see that this is a very generic kind of arrangement. It's basically true of any scientific process. So whatever you're doing yourselves, try and map what your area is onto this, and you'll see that there are parallels with basically any area of analysis. So you start off with some theory. In this particular example, the theory is a cosmological model characterized by order 10, 20 or so parameters. I mean, the other is just 6, but that's for order 10. So you've got, for example, cold matter density, baryon density, dark energy density, whole constant currents associated with the initial spectrum fluctuations and so forth. And one has this set of parameters, this space of order 10D, but what one wants to do is one wants to map that into an observable. In the case of the CMB, that observable is most usefully the cosmic microwave background power spectrum, which just gives you a measure of power on inverse length scale. This is characteristic of Google, which I can explain at the end if you want to, but I'm sure everyone knows what that is anyway. And the process of getting from theory to observable is via some package, either CMB fast or CAM in this case. But the idea is that this process can be quite computationally intensive. In other words, going from theory parameters to observable can be an intensive task. This particular program has to, for example, calculate a set of couple of Boltzmann equations for the Bayesian distribution function as the universe evolves, and that can be quite computationally intensive. Now, the other side of this figure, you have the experimental setup, you have some measurements of the sky, and you get a measurement of CMB. This process is non-trivial, but I'm not going to discuss it in this talk. And so you have a measurement with noise, perhaps correlated, of your observable, and so you then need to compare these via a likelihood function. So you have to evaluate the likelihood function. And then that likelihood function you evaluate, you explore the space of parameters, evaluating this, and you map out a distribution. If you apply it, it becomes posterior. So that's the basic thing that people do in CMB analyses, and I'm sure it's something that you all recognize from your own analyses with different names associated with it. There are some problems with this approach. Well, not so much problems as there's pains in the neck. It can be slow to perform the likelihood evaluation. So it can take several seconds per point, for example, to perform the prediction of the observable power spectrum itself. Equally, the likelihood functions, they're not just simple chi-squared. Some of them, particularly at lower resolution, have high correlation, but the correlation matrices with non-trivial off-diagonal elements, which makes the calculation slow. So the actual likelihood function itself can be time-consuming, an order of 2 seconds. And so when you're moving around these spaces, the space of your model, in this case cosmological model, you can require 100,000 points to get a reasonable sampling set. And so these things can easily build up into taking, quite a number of CPU days. You can perform the analysis in a day or so with a few cores, that's fine. But if on top of that you want to do model selection, then the standard methods for performing that typically require order of about 10 times the number of samples as parameter estimation, the technique that's the MCMC technique used to perform that evidence integration. And so you can end up taking many millions of these points, and it becomes quite a burdensome process to explore the space. And indeed, some of the applications I'll show you later on in particle physics, actually doing it this way, they take several CPU years in order to converge. Another problem is that you might get incomplete exploration of the parameter space. Some likelihood functions are complex, and their corresponding likelihood of posterior distribution is multimodal. Okay? So obviously gradient search methods will just go to a local optimum, but even conventional MCMC methods can find multimodal distributions quite a challenge. This is a constrained minimal supersymmetric standard model analyses, which actually has 8 additional parameters, but I've just projected it down into 2 MSSM parameters. I don't think it's not really called what they are. They're just used to illustrate that this 8D box projected into these 2 dimensions has quite wide separations between nodes, and they're all physically interesting. Okay? They're all different parts of the parameter space, which particle physicists are interested in. So you can get very low sampling efficiency with, say, standard metropolis Hastings. So in order to try and speed things up a little bit and explore the parameter space, we've been working with nested sampling. So here again is the plot I just showed you for the standard CMB analysis. And to be perfectly honest, this analysis you can perform very easily with 10 lines of code, standard metropolis Hastings sampler, because it's a kind of a few-dimensional unimodal multivariate guess. So this is easy. This is not a map of the sky. This is actually a posterior distribution. And it's a posterior distribution you get when you project the posterior in position, amplitude, and size for SN clusters embedded in the microwave background. You project that just into these 2 parameters. And indeed, some of these are real clusters. This is the posterior distribution where the posterior equivalent being an object is large. Some of them are clusters, some of them aren't. I'll explain how to tell the difference shortly. But the point to take away is you're having to navigate a distribution like this. And that's more challenging. And also integrate under it to do model selection. So obviously the standard way to explore distributions is using metropolis Hastings. It's a very simple algorithm, and that's not meant as a criticism, it's actually meant as a compliment. Simple algorithm is usually best. and it's very powerful, but it does have some problems. I mean, the basic idea, again, I'm sure you'll know, is that you're trying to navigate some distribution, and you're at some point here, and you have a proposal distribution from which you draw your next trial point. And basically, if your next trial point has a higher P of X, you accept it. If it has a lower one, you may or may not accept it with probability by this ratio here, basically, for differences. So you can think of this in some ways as if you're trying to imagine yourself on I just came from Banff where I gave a talk, so if you imagine yourself in the Canadian Rockies, blindfolded, so you're blindfolded and you're trying to find your way to the highest peak in the Canadian Rockies, and you take a step randomly, random direction, distance distributed with the Bayesian, say, and if you put your foot up, then you take it, you put your foot down, you may get there with the probability of how far down you place your foot. Okay? And you walk around, and that will, there are theorems that prove that will eventually get you to the peak of the Canadian Rockies. We'll sample from that distribution, and many of the samples will get you in the region of the peak of the landscape. So that's fine, it's easy to use. I mean, that's the pseudocode for it. It really is just a few lines. But it does have issues in two domains. It has issues when you have, for example, a long degeneracy. I mean, this isn't a long degeneracy, but long degeneracies are larger than this building character space, but this is just an illustration of one. And you can see that has a problem, because if you're trying to move quickly in this direction, so you want this to be large as possible. If this is as large as possible, this proposal, lots of your points in the orthogonal direction are rejected. So you end up essentially just diffusing them like this, which is slow, because diffusion time goes to the square of the ratio of these two deficits. And that's just a 2D, and then it gets much worse. It goes to the worst ratio. Also, it's particularly bad for multimodal distributions. You're trying to sample from this, say, and you're sat here, and you're sampling, and you're diffusing up here, as I just described. But you need on this illustration, you go 1, 2, 3, 4, 5, 6, say 7 sigma draw from your proposal to get to here. Those are rare, of course. And what's also damaging sometimes is that your standard convergence statistics, and the algorithm statistics, would look beautifully converged if you're just moseying around here, because it's never seen this point. So your convergence statistics will not tell you this. So there are some obviously a great literature on how to adapt the basic Metropolis Hastings algorithm, and enormous literature on it. Some very clever stuff in here that I would recommend anyone to read up on, because some really good stuff here. I won't go through it, it's not the purpose of the talk, but just to describe, you can set the proposal width to achieve a certain acceptance ratio, usually order of half, dynamically during the burning process, but you've obviously got to remember to fix it thereafter, otherwise you're not drawing the target distribution. You can have multiple change, just starting from different points, and hope to cover parameter space that way, although it's not guaranteed to. You can try and bring in the function you're sampling from gradually, so you have some temperature essentially which dampens the whole function down. You can move around very easily, then bring in the function that you like gradually, your multiple peaks, whatever, will gradually come in, and hopefully, as that happens, you will get through some of the smallest foothills, but nonetheless, once the temperature goes past a certain point, you will be trapped largely in the local optimal you're in. Sequential proposal distributions, updating subparameters as time, example by Gibbs. And some really fun ones, Hamiltonian sampling, where basically the proposal distribution is you take a marble and you flick it in a random direction with a random speed, and you follow its evolution, just solving Hamilton's dynamic equations for a certain period, and then where you choose to stop the trajectory is your next proposal. So that's kind of cool. You can go along to genesis quite easily. Slice sampling, genetic algorithms. So there are various ways in which you can it all comes down basically to finding innovative ways for setting the proposal distribution. So these are fine, and they can work very effectively in some problems. But in our experience, they are quite problem specific. You do have to spend quite a lot of time tuning them to your particular problem. So we were interested in seeing if there was a way we could do something that didn't require tuning on a problem-by-problem basis. So we explored the idea, happening for some years now, explored the idea of nested sampling. Now, some of you may have heard of this already. It's been around for a while. My good friend John Skilling came up with it nearly 10 years ago now, astonishingly, after a visit to Cambridge. So the idea is quite simple. You define this quantity x, big X, which is the prior mass, that's the fraction of the prior, right, that lies above a certain likelihood level. Okay, so the likelihood lies above some limit lambda, and it's the fraction of the prior lying above the likelihood contour lambda. And you can define this as this. Yeah. And the nice thing is then that the really hard thing about Bayesian methods, basic calculation, is calculating the evidence of this integral. Okay, this can be a really, really time-consuming job using thermodynamic integration, for example. And so the nice thing is that by defining this variable, you basically do a coordinate transformation, for which the Jacobian is calculated to trigger different this. And you take this multi-dimensional integral over the Cantor space, you turn it into a one-dimensional integral over this quantity here. This is why it's what it means. And we know how to do one-dimensional integrals. We just do the standard quadrature methods, and even something as high school trapezium rule works fine. So this is the nice neat thing about it. So that's the first thing. So you do this. But in order to get your samples, the approach is as follows. Let me just go through this, take a little time to go through this. So this is the kind of core of nested sampling. And again, some of you probably know this, I apologise, but some of you may. So you start off, you set your iteration count to 0, and here's my space, just imagine 2D, for example, 2 counters, 3 counters, 2, and here is my prior domain, okay? And for simplicity's sake, I'm going to assume that the prior is uniform in this white box. So initially, the prior volume is 1, obviously, it's normalized, and your evidence counter is 0. So the first thing you do is you sample endpoints, randomly draw them from the prior. Okay? Note you're drawing them from the prior. Priors are usually straightforward. They're usually, they're often uniform, but they're usually analytic, so these draws are usually very straightforward. And you calculate their likelihoods. Okay? Update the count. Then what you do is you find the point with the lowest likelihood value. So here it's the point in green. Now, that point defines a likelihood contour. Okay, so there's a contour that passes through this point, obviously. The contour with the likelihood that this lowest likelihood point has. Now, you don't know that contour, of course, a priori. You don't know it. And so, therefore, you do not know what volume is contained within it, i.e. the shape of it. However, the prior volume, however, you do know the probability distribution for it. Okay, because the remaining prior volume at a new iteration is just some multiple of the prior volume at the previous iteration. And essentially you're just picking the largest of a set of numbers drawn uniformly. And that has this probability distribution. So you have a probability distribution given n for the amount, the fraction by which the prior volume shrinks.
And is n just a random number?
So n is the number of points that we're sampling here, and I'll go through that a little later on. The larger the number of points, basically the higher resolution, you can be certain that you've explored the parameters. So one then increments the evidence by the value of this likelihood, and essentially the amount you've moved in, and then you remove this lowest likelihood point from the set. gone away, and you replace it with a new point, again sampled from the prior, but this time with a constraint that it lies within this region here. Okay? So obviously when you draw a point, you can calculate its likelihood value, and you can figure out whether it's got a likelihood greater than or less than the point is thrown away. If it has, then it's within this contour, and so you accept it. And you continue, and you come in essentially higher and higher and higher until the the correction you get to your evidence drops below some tolerance that you set. Okay, and then you stop.
So let me just 1 second, if I may show you it working on a problem.
Okay, so this is nested sampling. It's starting off in the wings, gradually moving up into higher and higher nested probability. This is an example with multiple modes, and it gradually goes up each mode to the top until it calculates the remaining contributions to the evidence are below the tolerance I want, and it stops. Okay, and this is a multimodal egg-box distribution.
Okay. So it's
the way to think about this in terms of my climber analogy is you can think of each of the live points, each of the n live points that I just described as a climber again. But this time the climbers have GPS, okay, to tell them where they are in that latitude and longitude. They have an altimeter to tell them where they are vertically, likely value, okay, and they have mobile phones to tell each other all that information. Right? So that's why it's quite useful. That's why the algorithm is very good at navigating quite complex distributions. So there are certain NCFC techniques that are similar that are used on samples of points. So if you think of nested sampling, it's coming from that path. So but it's this use of samples of points that talk to one another, and the more global rather than this local walk nature of Manila and Metropolis Hastings, which makes the algorithm a bit different and quite effective. So the advantages of the algorithm are that it proceeds exponentially fast into high likelihood regions. Typically, the prior fraction of the ith iteration is e to the minus I over the number of live points, roughly. Okay. And in all of the applications that we've tried it on, in cosmology and particle physics phenomenology, it comes out at around about 100 times faster, both in terms of parameter estimation and integration. So it takes basically 100 times fewer samples in order to navigate the distribution and calculate the evidence.
And that's independent of the number of dimensions.
Yeah, well, so at the moment, the algorithm itself can work in going up to high dimensions. The particular implementation I'm going to describe mostly kind of bails out at about 100, 200 dimensions. But we have algorithms that now go up to a few thousand dimensions. But you can never do, for example, CMB map estimation, CMB sky estimation stuff, which is millions of dimensions. For that, you have to use other algorithms. Yeah, so I mean, I use Hamiltonian sampling instead of cube sampling to do that particular problem, which is more flexible for the sampling. But there are other methods for that, because that particular problem is tens of millions of dimensions, but it's a large unimodal blob. Okay, this algorithm is for, say, hundreds of dimensions, but lots and lots of spikes and curves and things, which is what you tend to get in particularly particle physics. So there are some technical points here. There are some problems that this can actually solve that thermodynamic integration can't solve. Problems that exhibit phase changes that the annealing schedule. That's quite technical for it. The other nice thing is that the whole algorithm is built to calculate the evidence, but because you draw points uniformly in the space of L and X, the prior volume, then immediately you see that if you, at the end of the process, if you take all of the samples you gathered during your nested sampling algorithm, and you weight each of them by essentially the amount it's adding to the evidence divided by the total evidence at the end of the process, then these samples are posterior weighted samples. So you get the posterior samples for free at the end of an evidence calculation. So nested sampling kind of reverses the priorities that are present in MCMC. MCMC generically is primarily rather a parameter estimation algorithm for exploring the distribution of posterior samples, and you can get evidences by doing things like thermodynamic integration. You have to play with them a bit. Nested sampling is the other way around. It's an evidence calculator that, as a byproduct, gives you posterior samples. Right, so there are the most challenging task at each iteration of the nested sampling process is to replace the lowest likelihood point that we've removed with another one, if you recall, that's sampled from the prior, but within what could, in general, be quite a complicated, hard-edged region defined by the likelihood contour of the point we just removed. Okay? Now, one can perform this sampling task itself using MCMC. One can do that. We've played with that for a long time. It works very nicely, but in other words, it gets the right answers, but it can be very inefficient. You start re-inheriting many of the problems that I just spoke about with MCMC itself, particularly when your hard-edge likelihood distribution is degenerate, curves, or multimodal. In other words, you have patches in the likelihood space. Again, you hit the problems I just described. So there are various ways of doing this. The first thing we've implemented, which has actually been out for a few years now and used quite widely, and I'll describe some new developments later on, is something based on analytical rejection sampling, which sounds insane, but actually works surprisingly well. So what we do is we build a tailored band to this surface, and we actually use an algorithm from computer vision, which builds convex hulls around any shaped object. Essentially, it was built originally for collision detection in computer games. And it's a multi-ellipsoidal band with a variable number of ellipsoids, you don't define that. It maintains the total volume to exceed the expected prior volume in any iteration, which remember you can calculate the expected prior volume, so it avoids runaway shrinkage of the set, which would be a possible. And one can very cheaply determine overlaps between these ellipsoids, and indeed, if you think about it for sort of 5 minutes, if you have a set of overlapping ellipsoids and you want to draw uniformly from them, you can actually do that analytically. So here is an example of the band calculator. If this were a set of points, here are the bands calculated by the algorithm. And here you've got a set of points drawn uniform for a torus. And here are a set of, here's a multi-ellipsoid band for those points. And one can draw from these, and these are tailored to the surface. So the idea is it's kind of bootstrapped, essentially. At each iteration, you have a set of points. You're only throwing from within your likelihood region. You're throwing the lowest likelihood point away. So you take this set of points with this band applied to it as the region where you want to take your next one. So it kind of bootstraps its way through. And the reason you can do this is that nested sampling is always going inwards in probability, always going in and up in likelihood. That's why you can use it here and not in other algorithms.
How many of those ellipsoids do you have?
You can have 1, 10, depends on how many nodes you've got. So if you've got, say, 300 nodes, you can have 300 ellipsoids. Or if you have long degeneracies. For these problems, I'll talk to you how many it's got for these, and you'll get some idea of that. So it also has for multimodal distributions, it also has an algorithm that we developed to identify which samples belong to which node. So we have an automated node identification algorithm. Okay? And so here is it applied to that's the problem I just showed you a little cartoon of. Here's what we call the ink box. It's very straightforward to the problem, it's just an illustration. And here are samples that Multinest has taken, color-coded by the algorithm, not by hand. So, and it basically can tell when you get a separation of nodes. And that's nice because sometimes you don't want to perform an estimate over the whole thing. You might be interested in the constraints provided by this node of the posterior. Equally, you might be interested in the evidence in this mode, so the integral just under, say, this purple one. So the mode identification algorithm performs its separation automatically and allows you to make isolated sort of local inferences, either of parameters or of integrals evidences under that. And it's all done in a way so that the local evidence, some of the local evidences are automatically equal to the total integral of the whole thing. So we keep that as a constraint.
So the first example that you showed, the animated that you showed, that gives us the position of the key data, but it doesn't give us the full.
No, it does. No, it does give you the full one. So it gives you the full one. Let me get that back. Let me try and redo that. No, wrong one. Let me just relaunch it.
Because I mean this final stage.
So if you look at this, it's sampling, when it's in this region, it's giving you the wings, and when it's in this region, it's giving you the lows. And it's just that it does all of its work at low likelihood first. So it works in a kind of likelihood order. So all of the inferences that are drawn from the points in the posterior at low likelihood happen early on, and the algorithm moves up in likelihood up these.
So you should keep
I'm sorry, yes. So I did say that, but it might have slipped through the net. Yes, you keep the entire set of samples, the entire history of samples.
What's happening to the peak on the very left? Seems like it's gone.
I don't know. Maybe it has. I can't see.
Might be wrapped over here.
Yeah, I think it could be wrapped. I don't know. It's got a point here. See, it has a point here. It's populated these here. I think it might be wrapped over to here. Okay. I don't know what's happening. I think it is the wrapping. I think it's. Yeah, I don't think the wrapping is actually right. I don't think it's centered right because this is tipped over. But I think they're over here. Sorry.
And is there a test that convergence test, when
So the convergence test, if you recall, is you can calculate the, so at any particular point, the largest contribution that you will get to your evidence is the maximum point, the maximum likely point in your remaining set of samples times the prior mass at that iteration. And if that is less than the accumulated evidence so far, with some tolerance factor in, then you stop. Okay. So here's the egg box again. That's the actual function. And this, you can calculate this analytically, the evidence. That's why the evidence comes out fine. I've just shown you the demo. For problems that, and that one, it had this many ellipsoids. Okay, as many as you see the egg box. Here's something that's meant to be as awkward as possible for the algorithm. So this is a really nasty problem where you take a very, very thin Gaussian. So the cross-section of these shells is in fact a very razor-sharp thin Gaussian. You wrap it round on yourself. Oops. You wrap it round on yourself, okay, to make it a highly degenerate problem. And then you make it multimodal as well by putting another one. Okay, so this is something that we thought was optimally nasty. And so you're having to build up these bounds around its edges. And this is hard to sample from with MCMC, very hard to sample from MCMC. So MCMC sampler, in order to get evidences at the accuracy that we wanted them, say 0.1, here, you needed about 1 million samples using a sort of an average bank sample, which is pretty good in 2D. We needed just 7,000 using our, and here are the points, the set of points, and the mode algorithm is separate, the mode separation algorithm obviously worked. And so you can see the points follow nicely, the distribution, with high efficiency, and indeed even up into 30-dimensional versions of these, the efficiency stays, tolerable. And the evidence is command correctly. You can also calculate the evidence with this analytic, which is why we built it. So kind of, some toy basically, 30D version of this, that's starting to get pretty nice.
How do you define the efficiency? Sorry, what's the efficiency?
This is the number of fraction of points accepted. So, multi-nest has been used by quite a number of areas. This isn't all of them, this is just what I put on one page, but the idea here is just to show you its gravitational lens in particle physics phenomenology, using it a lot now, configuration physics cosmology, supernovae, or something. So it's kind of, it's been used, it's freeware, so you can download it or you can use it. And it's been worked and tested against MCSC in about 200 different applications now, and this has worked very well. There are a number of applications which I can just take you through very quickly because they're kind of interesting. But here's a toy object really, just to illustrate. Let's say you have a set of objects, and then you vary them with some noise. Since I've given you this, you'll be able to persuade yourself you can see where they are. If I just gave you this, you might actually see some fake ones as well. And this is just a toy problem. You have 4 parameters: the position, the amplitude, and the size of the object. And actually, trying to navigate the resulting posterior distribution, here it is projected into the position space where you've marginalized through amplitudes and sizes, then this takes about 5 million samples using a very, very good MCMC sampler and thermodynamic integratable basis. But it's about 100 times faster using multi-nest, more efficient using multi-nest. You can see here this multi-nest, say, points projected into the position space, and the mode separator is identifying these points. So each of these points corresponds to a peaking probability for the model that there is an object. And what's nice is that you see each of these points identified, and also, of course, as well as getting estimates from each point, so each of these you can calculate posterior estimates from each lobe separately. In other words, the properties of the object. Obviously, you don't want samples from here to be folded into a calculation of the properties of this object, so that's an example of why you would like local inference. And also, you get the integrals under each of these, i.e. evidence under each lobe, and that local evidence, as we call it, provides you with a means of performing model selection to tell you what is the probability that each of these lobes corresponds to a real object. So you don't only get the parameters for your object, you get a probability that the object is real. And this is actually used in planet clustering. So we've performed lots of other cosmological things. We've searched for textures in the CMB. The CMB has a kind of a big cold spot down here that you might think could be due to an unwinding topological defect. It probably isn't, it's funny. The point is that you're searching for localized objects across the whole sky. Here's the sky rolled out into feature of phi, again integrated through the parameters associated with the defect profile and why the defect profile. And again, you see it's a nasty posterior distribution. Okay, this is projected down. There are 5 dimensions that I've projected out of this. It's just projected into the position space. And each of these corresponds to a putative cluster. This corresponds to the cold spot cluster. And indeed, this has an evidence over the null evidence of the object, which is that view, i.e. it corresponds to an object. And there are other ones there that I won't go into too much detail, so we haven't published that yet. We use it for finding SN clusters, as I say, in the CMB. So the SL dome effect, just inverse quantum scattering of the CMB of hot intra-cluster electrons, which takes your black body distribution and shifts it to higher energy. So if you observe it like we do largely in Cambridge with our instruments at lower frequencies, it becomes predicted. Looks like this. And it's a decrement embedded in primordial CMB fluctuations. We observe it with an instrument in Cambridge called the Hartnett microcount imager. We also observe it with Planck, but this particular example is our own instrument, which is just outside Cambridge. And it's not easy to interpret the maps you get. These are actually simulations to show you that the maps look quite similar. This is a map which has confusing extragalactic radio galaxies in here, which are peaks, positive features. We put one very close to the pointing centre, and there is no cluster in this simulation. There is a cluster in this simulation. You can just about make out this. But the algorithm itself hunts through the Fourier data and samples from the distribution and can calculate the evidence that there's something there. Indeed, it's a very huge detection. But it's just the fact that have a lot of computing that you can model well. And you can then navigate the distributions of the cluster parameters, mass, temperature profile, and so forth in the usual fashion. Indeed, it's used on a daily basis to do AMI analysis. Here's an example of an AMI observation of April 1423, and here's limits on, in this case, a total mass. It's a beta model, the curvature, the size of the core, and its fraction of the gas fraction. So it's used on a daily basis to find and characterize the cluster. It's also applied to weak lensing. So again, you can only see in simulation how well the algorithm works. Here's an input of some clusters. You take them through a lensing simulator. Here's sort of the best of the rest algorithm for reconstructing the convergence distribution. This is a maximum entropy reconstructor. And here's our sort of multi-nest powered Bayesian object finding algorithm. It's also been applied in gravitational waves, so for both real LIGO data and also simulated LISA data, or whatever LISA will be called. And it's very good again. Again, you're looking for patterns. This time they're not objects, student objects, they're particular waveforms from gravitational wave sources like binary black holes, but they're buried deep in noise in these laser interferometers. And again, we won some data challenges using this approach. It's very, very good at navigating what is a very complicated distribution in around about 10, 20 parameters describing the waveform. Okay, so it's kind of used quite widely. Being applied, as I say, to real LIGO data. We'll let you know when we find something, obviously. Nothing yet, but it's used on a daily basis. And some other stuff we've done for a bit of fun, because Farhan, Feroz and I aren't really planetary scientists, but when we did the LIGO analysis, we thought, looking for signs of planets in, for example, rate of velocity or transit data is the same problem mathematically. So we've applied it to that. And indeed, we've taken public data and found new planets. And because we have this evidence calculator, so it can navigate distributions well. Here's a snapshot of some data, and here's the rate of velocity we expect for this 6-planet solution. We've actually extended it now, so it doesn't just use Euclidean physics to use embodied dynamics to behave resonances and so forth. And we're extending it to transit data as well, to rate of velocity. So we're very good at navigating distributions. It simply works nicely. But the point is, we can use the evidence to determine the number of planets. So again, we increase the number of planets one by one, and then we take the evidence for our solution to, when we find the peak in that, we stop and say that this is the peak. So here is an example, which is another star with 2 planets around it, where there is clearly evidence that 1-planet solution is terrible, the 2-planet solution is very good, the 3-planet solution is too wrong. When you can fit it, then you have loads and loads of parameters that are well constrained, the evidence for either parameters. It's also been used a lot in particle physics by us and by others. Mostly applied to SUSY phenomenology, in particular looking at the minimal supersymmetric standard model extensions, both constrained one and phenomenological ones. And this is where I took the example earlier on from. Again, it seems quite capable of navigating these distributions. And I'll come on to it a little bit more on that in a second. So that's the basic multinest, which is out now. Just in a couple of minutes, I'll take you through some new stuff that we're about to publish in a week or so, and we will add, there is a version of multinest that already includes this, but obviously it's not public, it will be public soon on the multinest time. And this is a new idea, or an extension, called importance nested sampling. So it's an extension to the basic nested sampling algorithm. So let's take some generic problem. We're trying to estimate the expectation value of some function under some distribution. Obviously, if you can calculate samples easily from the distribution, then you can just calculate the expectation value trivially. But if you can't, then you can try importance sampling. Importance sampling is just you have some other simple distribution, okay, and you take samples from that, and you find these weights as the ratio of the distribution you can sample from the distribution that's tricky you can't, and with those weights you can get this expectation value. So that's standard importance sampling, which you'll know, I'm sure. But you can apply it in nested sampling. So you can apply it to calculation of the evidence. All right? And the nice thing is it uses all the points sampled by multiples. So even if in the nested sampling process a point is rejected, okay, you still have evaluated that point. You still know where it is in the parameter space, and you know what posterior value it has. So it seems a waste to throw it away. So what we instead do is we build a important sampling distribution. And after a bit of head scratching, you figure out the appropriate important sampling distribution to build is this one, okay, where over the iterations of the nested sampling process, you weight by the number of points sampled, with the live point of that iteration, which is usually constant, times the this function, which tells you whether the point lies in your unit of ellipsoids or not, divided by the total volume of your unit of ellipsoids. This important sampling function, inserted here, and it gives you an evidence estimate back. It's basic important sampling part of that. You have to think a little bit about what the important sampling function is used. And that's nice, but because it uses all these points, it's very efficient. So here's the example I showed you earlier on. These are the results I showed you before. Okay, so it gets the answers, again, just as well, but you see, for the same number of live points, the accuracy, particularly as you go up in dimensions, is getting better and better and better. So typically, you get an order of magnitude increase in accuracy for the same number of live points, or taken the other way round, you can get the same accuracy for about a tenth of the number of live points, and so you get about an order of magnitude increase in efficiency over standard nested sampling. Okay? And because you're using all the points, you're not dependent on expected product volumes, and that's where the increase in accuracy comes from. So this is a new sampling technique, obviously inspired by nested sampling, now coded up in a new version of Hobson that will be released shortly. This is something that we're also working on in terms of nested sampling, which is not. It's tested, it's coded, we're testing it. The release for this will probably be over the summer, because there's still something we need to do. So this is going back to the start here, throwing away the ellipsoid bound approach, which only works up to, say, 100 or so dimensions, and trying to get something that works in much higher dimensionality. So just to remind you, you're trying to sample from the prior, say U4, within this, the likelihood contour, let's say it's I said you could try and generate a point with MCMC or sort of bands, whatever. The MCMC approach is slow, it takes a long time to diffuse to get where you start. So we tried basic Hamiltonian Monte Carlo, but that doesn't work for various reasons. So what we in fact ended up doing was using Neil's idea of reflective slice time. So it's Hamiltonian Monte Carlo on a flat billiard ball table with a few tweaks. So you start and you flick your marble, it bounces off the edges, and you take a point when you come back when you've done a few bounces. So the actual algorithm works like this. You start here, you proceed to a particular point. If you go outside, you reflect relative to here. So this algorithm needs the gradient of the posterior as well. And that will usually get you to reflect back inside, in which case you'll take the point. Sometimes you won't reflect back inside because you've gone too far here before you notice you've gone outside the boundary. So then you backtrack to here and reverse your direction. It's reflective slice sample. And it's sort of billiard ball Hamiltonian sample, essentially, with some extra tweaks to make sure you get back inside the region. And this works pretty well. Okay? There are a couple of parameters associated with how far you jump at each step, which require you they don't need to be fine-tuned, but you can't set them in a crazy way. That's largely what we're looking at the moment. We're trying to figure out guidance for the user for setting this single parameter essentially. But it's quite robust, and it works at the moment up to several thousand dimensions. And the reason that we're, even in multimodal cases, and the reason we want to do this actually is we want to be able to navigate the free energy services in protein molecules. And they're typically a few thousand dimensions, and they're highly multimodal with thousands of local minima where you misfold local free energy. And so this has a chance, I think, of doing it, which dimension question.
So, multi-dimensional.
It's too large. So once you go over 100 dimensions, 200 dimensions, multiness slows down because, well, it's easy to see why, because as you go to high dimensions, all of the volume in ellipsoids is packed at their edges. Whereas this approach doesn't have that problem. So for nasty, low dimensional, 100D or less broadly, use ellipsoidal. For 1,000 dimensions, standard multiness will just grind to a halt. But this approach kind of works.
So let's say for 60 dimensions, this is more expensive than the multi.
It depends a little bit on the buyer. They're about the same. In 10D, this is more expensive. When you get up to about 100D, it kind of becomes around about even. When you go to several thousand D, multiness just runs the problem. So here is Rosenbrock problem. It's an illustration of an elastic degeneracy line. This is just a 2D one, but we've gone up to several hundred dimensions in this one, and it works very well. I think this was the 100-dimensional example where we calculated the evidence in this 100D Rosenbrock function. And we've gone up to thousands of dimensions in the Rosenbrock, and it works fine. So that's an example of it working on the degeneracy line. Here's an example of working on multi-modes. This is the raspberry gradient function. Seems if you want to function it after, you have to have an exotic name that begins with R. So it's highly multimodal. Again, this is just in 2 dimensions. It works fine. We've again got up to several hundred dimensions in the raspberry function, and it can navigate these multiple absolutely fine. So in the last sort of 5 minutes or so, I'd like to run you through something that's not to do with how you navigate the space, but it's to do with, at each point that I've been showing you, you need to calculate the likelihood function, or posterior, the prior already calculated, which says the likelihood is least. And so we decided that we'd try a machine learning approach to try and speed this up. So we've used neural networks, we've used the simplest kind of neural networks, we've used feed-forward networks, with input layers, hidden layers, and output layers. You may have more than one set of hidden layers. And networks are very easy beasts. They have nodes which receive information via weighted connections and process them according to a nonlinear activation function in the hidden layers and a linear identity function in the output layers. So each layer is just a nonlinear tweaked linear sum of the previous layer until you get to the output layer, which doesn't provide the activation function. And they're really nice because they provide mappings from this set to this set, which can be reduced to an arbitrary mean square accuracy for any L2 normalized function, provided you have enough hidden layers. So there's a universal approximation of the image, which makes you feel comfortable. And so what we did, let's take the cosmological example. Remember I told you that going from the cosmological parameters to the observables required you to use Campbell CMD files which solve this hierarchy of this Hobson distribution function problem, which is a pain. It takes 10 seconds to point or something. And what we did is the inputs here are just our cosmological parameters, so there are like 10 of those, and the outputs were say 1,000 points in the CL spectrum, power spectrum. Okay, so you're training the network to learn this mapping. And the mapping, the outputs, we actually had temperature and polarization versions of this spectrum. We also we trained separate networks for each, it's just easier bookkeeping-wise, and then we trained another network for the matter transfer function, and we trained other networks for the individual likelihoods themselves of the big experiments. Obviously, Planck, we haven't done that yet since we were about to start working on that slide. And what you find is that you get a speed up over CAM of around between 100 100 to 10,000 times, depending on the cosmological model, depending on how baroque your cosmological model is. So here's an example. We just learned, to make life easier, 7-parameter non-flat lambda CDM model as an illustration, but we've learned other far more complicated ones than this. Here is how the power spectrum changes as you vary with certain cosmological parameters. Do that. And you train the network with a few thousand points, which you can do anyway, you need these anyway, and you essentially define a network misfit function. We optimize this using our neural network code, which is the paper is going to be out shortly as well, called Skynet, which trains networks, a generic neural network training algorithm. And we have a network, okay? So there are two things you can do. We first took the network that took the parameters and spat out the spectra, the CMB spectra, and then we input those spectra into the standard particle codes. And I can't actually remember what the red and the black are, but one is using just the normal approach, and the other one is using, in other words, spectra obtained using CAM, and the other ones are spectra obtained using network Skynet spectra. I can't remember which is which, but it doesn't matter. These are marginalized constraints on the cosmological parameters in the process. And you get quite a good speed up, okay? Particularly when you combine whole with multiple. But there is still a bottleneck because you're still using the standard likelihood codes. If you actually throw all that away and you use the Skynet likelihoods directly, then you end up getting a very, very profound speed up for say 300 CPU hours, combining with multi-nested down to about 10 CPU minutes. And again, the results look very robust. It's also able to learn the likelihood function not just at the peak, but way out in the wings, which you need for evidence evaluation, because the evidence integral obviously integrates all the way out to the wings, not just near the peak. And the evidence calculations, again, are bang on, no difference at all. And because evidence is a much harder thing to do with MCMC than nested sampling, the combination of networks and nested sampling gives you, again, starts to be really rather useful reductions in speed. I'll just skip through it. Here we've again applied it to SUSY modelling. Here, instead of CAM, the thing in the SUSY phenomenology world is called soft SUSY, and it basically takes theory parameters for your supersymmetric standard model extension, and the observable in this case is the sparticle, superparticle mass spectrum M. There are 15 sparticles in this particular model. And here, the process of going from theory to observable, in this case, is an iterative solution of a big nasty set of called renormalization group equations, i.e. it takes time. So we replace this mapping this time with a Skynet network, and these are the input, these are the true and Skynet estimated correlations for the sparticle mass spectrum, the different models, so they work nicely. And again, you get an order of 100,000 times speed up using the network over the original RGE solution. And so here we have a example which I alluded to earlier. This is again in the constrained minimal supersymmetric standard model, projected into a couple of dimensions just to illustrate. So here we have the neural networks learn supersymmetry, and we have also defining it with multi-nest to perform the exploration. And the original task using soft SUSY plus standard MCMC took 2 CPU years, and using the networks to replace soft SUSY and multi-nest to do the navigation took 2 CPU years and turned it into 1 CPU minute, which corresponds to a speed up of around 1 million. Okay? So it starts to become useful, and you can therefore explore far more models and investigate your data far more thoroughly when you don't have to spend 2 years doing it. You can just do it on something like that. So, just the last couple of slides. You can combine, I've already combined networks and multi-nest by hand, so to speak. I trained a network and then I use that network in multi-nest to perform the navigation. What we've also released is something that folds it all up for you and does it all at the same time, so you don't have to use Skynet and multi-nest separately. This is called bounding, okay? And the idea here is that you can combine Skynet and multinest. They're very complementary. And the reason is that if you think back to the little animation, in the early stages of nested sampling, the samples are prior driven, okay? So the samples are coming from a wide range of priors. So they're very good at training the network over the large wings of the likelihood. As you come in, you go higher and higher up the likelihood, and you have more points concentrated into the sort of more interesting regions, and so that is very good for teaching a network what the high likelihood regions of the likelihood look like. So you basically run multinest, and each sample you take you feed to another processor which Skynet is sitting on, and it learns the network. It trains the network that learns the likelihood function on an ongoing basis. So there's no calculation wasted. So you begin multinest, obtain samples, train the network, test its accuracy. If not, take more samples. If it's okay, use the network for sampling. Periodically use the old, slow likelihood calculator to check your consistency, to make sure you're not going out of your regime of trust. If not, ignore new samples, retrain. If you're okay, keep using it.
So it self-checks all the time. So you use this if you can already have the network training.
Yeah. So the point here is that there's no calculation wasted. So say you want to run an analysis problem. Say you want it using multiples. So you'd run it typically using the existing standard likelihood. Instead of doing that, you run it with boundaries. So the multinest samples are exactly what they would be anyway, okay? But they're just being fed to the network trainer. Once the network is trained, it will say, I know this well enough, and it will switch over to the network, and then the remainder of the inference problem will go very quickly. But it'll keep checking that it's still not accurate, the network is accurate. And typically you get a kind of a modest 50% improvement in speed the first time you do it. So you don't lose anything. I mean, multinest is fast anyway, and bounty is a bit faster. So you gain nothing. If you lose nothing, you gain a little. But at the end, as a bonus, you have the network trained. The other nice thing is you don't have to make any choices for regions to train the network. This algorithm will train it over the entire prior space, because the samples are being chosen wisely by multinest. You're not just doing a grid of points, you're taking a multinest point. The subsequent analyses, of course, you have the trained network. The subsequent analyses, you re-inherit the factors of tens of thousands. So it's just easy, and there's kind of no fat on it, basically. It's pretty easy in terms of the number of calculations. And it works kind of nicely on real problems as well. Here is multinest navigating raster and gas and shells and so forth. And it is boundary navigating it, so show you that it's learned distributions. You can apply it to cosmology, and there are black dotted and blue stuff here, and black solid and blue dotted lines up here. For a CMB analysis, LSS, CDM. And it learns it very well. The evidence is also very good. Again, the primary speed is just a factor of about 50%. But in every other analysis you do, you have a network trained for lambda CDM. And these data set of these then become order 10 to 4, 10 to 5 classes. So, in conclusion, probably a couple of minutes there. Standard Bayesian analyses can be very computation intensive. I think nested sampling in various versions to get your next live point is a very efficient and robust means to navigate distributions, which can be multimodal or have large curving non-degeneracies. And also very good at calculating evidences. I mentioned that you have this nice property of being able to isolate different modes of the distribution to perform local inference. And all of the problems I've discussed, about this paper and all, it comes in around 100 times. Networks, or your favorite machine learning algorithm, Gaussian processes, what vector machine learning you want to use networks because they're just really easy to understand intuitively, can provide large speedups. For the cosmological problem and the SUSY fitting problem, they both came in at around 100,000 times faster than either the Hobson code or the renormalization code that was used previously. So the combination of this over sort of the generic approach can give you speeds we demonstrated one example of up to 1 million speed. So multi-nest is available here. The importance nested sampling version will be available, I think, within a week or two. We'll publish a paper and we will update the version of multi-nest here to include importance nested sampling, which will give you a factor of 10 more efficiency over the standard version. And the Galileo Monte Carlo, that kind of pinball thing that I showed you, is coming soon, probably on the timescale of the slide, I guess, and will also be put on this. Bambi is available here. It uses Skynet to train the networks, but the standalone Skynet will be put here, again, hopefully in about a week or so when we get the Skynet paper on the archive, which is just close to completion. And so, that's it. Thank you very much.
Does Skynet dynamically choose the complexity of the network?
Right, so you can get it to do that, but it's quicker not to. So what we do is
Every time you change the network, it's retraining, right?
Yeah. So what we do is we navigate the space of networks using the evidence. So for each network, you maximize the posterior fitting function, right? And then we approximate, in Skynet, you approximate the posterior by Gaussian, okay? This is millions of dimensions network, so you can't navigate them in size, you can't navigate them with more optimizers. Then we calculate the Gaussian approximation, use that to estimate the evidence for that network architecture, and then as you change the network architecture, you try and maximize the evidence for the architecture as you change the network. But usually you're just quicker to just try it through. Okay. It'll be pretty obvious, so it will.
So, this is have you compared the neural network with LIGO, LIGO?
Yeah, sure. Yes, we have. So what I said. We're more accurate and faster and require less memory.
This is
parameters for the impatient cosmologist.
Yes.
This is a because all the networks. Well, I mean, the generic network algorithm we've got called Skynet can train classification nets, whatever. But in this likelihood task, it's essentially it's just an interpolator. So Pico does a sort of multiple enable interpolation algorithm. But it's prone to emergent instability we found, and ours is more accurate and easier to train. And so yes, ours is better in terms of in cosmology.
And does it mean human supervision, or you just it would be green?
So the nice thing is with Bambi, it doesn't. So with Bambi, you say, right, I've got my data. It's the only thing Bambi asks you to do is tell it your prior state. Okay, that's it.
But you still need the likelihood.
You need a likelihood function.
Right.
But you have it anyway. So you have a likelihood function from what your experiments were. Right. So what you would need to do a normal analysis is all that Bambi requires. And then Bambi will go and just do it all for you.
What
Okay, so firstly, multi-nest was written in Fortran, okay, in 90. But there are C++, Python, and R wrappers for it. Okay. Skynet's written in C++, okay, and Bambi therefore is written as a mix of C++ and Fortran. The control routine is written in C++. You can get away with thinking it's all written in C++ because it's kind of all hidden behind wrappers.
Yeah, I was looking for the magic for Python.
There's Python, there's Python wrappers, there's Python. There is in fact, there's Python wrappers, PY multi. It's all.
Is the neural network training dominated by likelihood evaluations, or does it take extra time to train?
I mean, it's not that bad. It's let me just just a second. I think this is in a just 1 second. This was in a talk. This is not that old. It's just I was going back to Hobson. Right. So here we go. So Skynet is trained in a number of ways. So let me just this is a Sky talk I gave. Obviously. Well, you know, it's a network to be used on the sky. What else would I call it? So the training is done in two parts. So we have a function which, for regression networks, is just a mystery function. For classification networks, is a cross entropy. Okay, and we train it in two steps. We use Jeff Hinton's pre-training algorithm to get to near the global optimum, which is very fast. That just takes runs through back to the network, and then we optimize the objective function using an auto-regularized gradient search algorithm, second order Hessian free. So it uses second order. It's kind of a Newton algorithm, but you don't even have to calculate or store a Hessian. It's a Hessian free algorithm, but still uses Gaussian. So it's pretty fast. So most of it is no algorithm. And no, we haven't tried to, I know what you're going to say, we haven't tried to nest it. So that you try and train a network with a network trying to learn the network life. We haven't done that. Because that just seems like a recipe for disaster. But the Skynet is going to be out in a couple of weeks, and it's a generic neural network training code. Uses Jeff Hinton's pre-trainer. For auto coders generally, they're a real pain to train. And then our own sort of auto-regularizing second order Hessian free optimizer. And that'll be out in a couple of weeks.
Well, if there are no further questions, let's thank speaker again, and we'll head off to lunch.
Right.